The high price of EV-specific tires often makes car owners gasp when preparing to replace them, even making them question whether this is a massive scam created by tire manufacturers to earn exorbitant profits. On major automotive forums and social media, a rumor has been widely circulating, suggesting that as long as the vehicle weight issue is solved, there would be absolutely no difference in tire wear. Many owners generously share their experiences of installing regular ICE vehicles' tires on their EVs and feeling absolutely no difference when driving. This further deepens the stereotype that EV tires are an IQ tax. Most people believe that, as long as you choose a regular tire with a sufficient load index, it can handle the extra hundreds of kilograms of battery weight on the EV chassis, and there is absolutely no need to spend large sums of money on tires advertised specifically for pure EVs. In this episode, we will directly present laboratory comparison data from international third-party organizations and global tire giants, using the most rigorous scientific tests to prove that, even under the exact same weight baseline, there remains a decisive physical difference in the destructive forces exerted on tires by EVs versus ICE vehicles. Besides uncovering the true nature and core technology of EV tires, we will also delve into whether automakers have the opportunity to introduce a dedicated tear-saving mode via software updates in the future to completely overcome the tire wear problem. Finally, at the end of the video, we will share a few practical methods that can truly and effectively reduce tire wear and save you money. To unravel the mystery of tire wear, we must first face the most commonly misunderstood concepts directly, which is attributing all causes of wear solely to vehicle weight. Undeniably, because EVs are equipped with massive high-voltage battery modules, their overall vehicle weight is usually 10% to 30% heavier than ICE vehicles of the same class. This inherent weight disadvantage indeed causes the tires to endure greater downforce both when stationary and while driving. However, scientific experimental data directly breaks the myth that vehicle weight is the sole variable. When a famous German automobile club conducted a long-term tire wear test to eliminate the interference of varying vehicle weights, they specifically standardized the tire wear amount in their experimental design, converting it into milligrams of wear produced per ton of vehicle weight per kilometer. In mathematical modeling, this essentially placed the weight of EVs and ICE vehicles onto a completely equal starting line. Yet, even with the weight variable completely equalized, the test results still showed that the wear index of EVs was significantly higher. The German Automobile Club's report pointed out that after deducting the impact of vehicle weight, the core variable causing this difference lies in the completely different output characteristics of the two powertrains. When a traditional ICE vehicle's engine is running, it needs to go through the physical processes of intake, compression, ignition, and exhausted, and wait for the engine RPM to gradually climb, then pass through the transmission and drift shaft conversion before maximum torque can be delivered to the tires. This type of power delivery has a time lag and is relatively linear. Conversely, the power source of an EV is a motor. The characteristic of a motor is that once electrified, the instant you step on the accelerator, it can output 100% of peak torque without any delay. This instantaneous burst of extreme traction causes microscopic sliding friction, invisible to the naked eye, between the tire tread rubber and the road surface. With every start and every acceleration, the tires undergo this microscopic tearing and abrasion under identical loading conditions. This is the primary physical reason EVs accelerate tire wear. Besides the instantaneous torque during acceleration, the physical mechanism during deceleration, it poses an equally massive test to tire life. An independent emissions testing agency in the UK conducted high-resolution mass spectrometry measurements of tire particles generated while driving. In their analytical model that isolated the vehicle weight variable, they discovered another key factor causing EV tire wear: the bidirectional stress caused by the kinetic energy recovery system. When we drive a traditional ICE vehicle and lift off the gas pedal, the engine braking force is relatively weak, and the tires primarily remain in an unpowered inertial rolling state. At this time, the friction between the tire and the road is relatively gentle. However, at the same speed and weight, when we drive an EV and lift off the accelerator, the system activates kinetic energy recovery to increase driving range. At this moment, the motor that originally propelled the vehicle forward instantly becomes a generator, producing a powerful reverse drag force to slow the vehicle down. What does this mean? This means that during driving, an EV's tires not only endure violent forward tearing forces during acceleration, but also withstand powerful backward shear forces during deceleration. This frequent and intense alternation of forward and reverse stresses will subject the rubber tread blocks on the tire's surface to immense physical fatigue. Test data confirmed from the UK agency that the frequency and intensity of this powerful shear force endured by EV tires are far higher than those of ICE vehicles, leading to a massive increase in the peeling rate of treading microparticles. This not only shortens the service life of the tire, but also spawns more environmental issues related to tire particle emissions. To dispel the public's doubts that laboratory data might be disconnected from reality, the global leading tire manufacturer, Michelin, also conducted an extremely rigorous lab versus road comparison test. Michelin deliberately selected a vehicle model that shares a chassis architecture for both ICE and EV versions. By adding artificial counterweights to the ICE version, they forcefully adjusted the total weight of the ICE vehicle to perfectly match that of the pure electric version. At the same time, both vehicles were fitted with tires of the exact same model, same size, and same production batch, and simulated completely identical driving trajectories and logic in a closed test track. This was an ultimate blind test that excluded vehicle weight, tire compound, and driving habits. However, once the experimental data was released, it once again confirmed the cruelty of physics. Under the premise of identical weight, the tire life of the pure electric version was still 15% to 20% shorter than that of the weighted ICE version. Michelin's official technical documents explain this phenomenon in detail. Besides the aforementioned instantaneous startup torque and kinetic energy recovery, the EV's unique dynamic load transfer is also key, because both acceleration and deceleration forces of EVs are more abrupt and direct than ICE vehicles. The vehicle's center of gravity transfer during the moment of acceleration, deceleration becomes far more drastic. This frequent center of gravity transfer will causing the tire's contact patch to endure highly uneven instantaneous high pressure, further accelerating abnormal wear on the tire shoulders and tread edges. After understanding these profound physical differences, we can comprehend why dedicated EV tires exist on the market and exactly why they are so expensive. The design of EV tires must strike a balance among three conflicting physical limits. First, it must possess an extremely reinforced rubber compound and carcass structure to resist the mechanical wear brought by the motor's instantaneous torque and the heavy downward force of the vehicle body. Second, it must achieve extremely low rolling resistance. Laboratory tests prove that using low rolling resistance EV tires can significantly increase a single charge driving range by 5% to 10% for EV owners who generally suffer from range anxiety. This is a critical performance enhancement. Third, it demands ultimate silence performance, because there is no engine noise to act as a cover. Road noise and the cavity resonance inside the tire will be infinitely amplified inside the EV cabin. High-end EV tires typically have a special polyurethane acoustic sponge attached inside. Acoustic testing shows that this sponge can effectively absorb resonance at specific frequencies, significantly reducing the perceived peak noise inside the cabin by about 20%. Since we've confirmed that the culprit behind rapid tire wear lies in the EV's unique power output characteristics, an interesting question arises. If automakers are truly willing, in future software updates, to introduce a so-called tire-saving mode by modifying the vehicle control computer's parameters to limit power output, do we have a chance, on a physical level, to make EV tires wear exactly the same as ICE vehicles? The answer is yes, but this requires paying a tremendous price. This hypothetical tire-saving mode must achieve to core extreme adjustments at the software level. The first step is to completely seal away the motor's much-vaunted instantaneous torque. Engineers would have to modify the starting and acceleration power curves to be unusually gentle, simulating the linear and slow power output, the engine of a small displacement ICE vehicle, forcing the motor, under any circumstances, to only release power gradually, thereby completely eliminating the microscopic sliding friction caused on the tread by strong traction during the instant of starting. The second step is completely disabling the kinetic energy recovery system. When the driver releases the accelerator, any resistance from the motor is completely cut off, allowing the vehicle to enter an unpowered inertial gliding state, much like neutral gear. This would eliminate the deceleration shear force and fatigue damage caused to the tires by the motor's reverse drag force, if under the premise of identical vehicle weight. These two conditions were perfectly achieved via software. The EV's physical destructive force on the tires would indeed drop to the same baseline as traditional ICE vehicles. However, in real-world applications, this would face to huge drawbacks that owners would find hard to accept. The first fatal blow would be a massive shrinkage in driving range. The reason EVs can maintain astonishing energy efficiency in stop-and-go urban environments relies extremely heavily on the kinetic energy recovery system, which converts the kinetic energy of every deceleration back into electricity to recharge the battery. Once kinetic energy recovery is forcibly turned off to protect the tires, all this potentially recoverable energy would turn into heat on the brake discs and be completely lost. According to automakers' real-world test data estimates, without the assistance of kinetic energy recovery, the actual single-charge range in urban areas could plummet by 10% to 20%. Another unignorable consequence is the complete loss of the greatest driving advantage of buying an EV. Limiting torque output would make the entire vehicle's dynamic response extremely sluggish and unresponsive. Drivers stepping on the accelerator would only feel a weak sense of acceleration, completely losing the handling pleasure of an EV's brisk launch and direct, on-demand acceleration. To extend tire life, one would sacrifice the most precious range wrought by battery technology. At the same time, they would also have to endure a cumbersome experience akin to driving a heavy truck. In terms of overall vehicle cost and driving efficiency, this is absolutely putting the cart before the horse, rather than pinning our hopes on automakers releasing this type of tire-saving mode that castrates vehicle performance. It is better to look at the current state of EVs and find truly practical money-saving methods that don't require sacrificing too much. The first and most basic trick is to always maintain the correct high tire pressure. An EV's weight distribution and chassis geometries are extremely sensitive to changes in tire pressure. If tire pressure is even slightly insufficient, it will not only increase the tire's contact patch, leading to a surge in rolling resistance and wasting precious power, but it will also fail to support the heavy vehicle body, causing excessive flexing and heat generation in the tire sidewalls, ultimately leading to premature wear and scrapping of the tire edges. Developing the habit of checking tire pressure regularly every month and strictly maintaining the high pressure value recommended by the manufacturer is the lowest cost and most effective way to extend tire life. The second trick is learning to choose smartly. Regular tires with extra load or high load ratings and low rolling resistance. If you personally have a higher tolerance for road noise, feel that it doesn't matter whether there's acoustic sponge or not, and your daily vehicle use is mostly short-distance urban commuting, rarely needing to challenge the vehicle's maximum range, then you really don't necessarily need to buy expensive pure EV-specific tires. When selecting regular tires, be sure to check for the XL or HL extra load markings printed on the sidewall to ensure the tire's structural strength can support the weight of the EV. At the same time, you can refer to the values on the EU tire label and choose energy-saving models with rolling resistance ratings of A or B. While providing sufficient support, these types of tires can also offer good energy-saving effects, and their prices are usually much more approachable than models advertised as pure EV-specific. The third trick. It is strictly enforcing the maintenance discipline of regular tire rotation. Whether it's a front-wheel drive, rear-wheel drive, or dual-motor all-wheel drive EV, the driving wheels during daily driving, we must continuously endure the forward force of acceleration and reverse force of regeneration. This powerful bidirectional stress will causes the tires on a specific axle to wear much faster than the driven wheels. If left ignored, it's very easy to encounter an awkward situation where two tires have reached the wear indicator, while the other two still have extremely deep treads. Developing the habit of going to the shop for a front-to-rear tire rotation every 8,000 to 10,000 kilometers can ensure the wear progress of all four tires remains even. This effectively avoids the waste of prematurely scrapping tires on one side, maximizing the use value of the entire set of tires. The final and most human testing tire-saving secret lies in the owner's own driving habits. Since we know that instantaneous torque and intense kinetic energy recovery are the culprits of tire wear, then as long as we make our right foot On the accelerator, a bit gentler during daily commuting. Avoid frequent heavy-footed rapid acceleration. And set the vehicle's kinetic energy recovery to a weaker or more moderate mode, making the vehicle's dynamics smoother during deceleration. By having the driver actively tame this pure electric beast, one can, without modifying system parameters or losing driving range, achieve the most direct and economically beneficial race-saving effect.